Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about three machine learning methods: bagging, random forests, and boosting. These methods are widely used because they often achieve very good performance in practice. They are all based on the same philosophy. They are combinations of simpler models, typically regression trees or classification trees. The key insight is that these combinations usually achieve much better performance than the individual simple models that compose them. Let's get to it. We're going to talk about three ensembles and specifically about bagging, random forests, and boosting. But first, let's start by reminding ourselves what trees are. Trees are interpretable nonlinear models for regression and classification. And the problem is that they suffer from overfitting. In this video, we're going to focus on the regression problem, but essentially everything we say can be easily adapted to classification. We're going to use a running example where we try to estimate the temperature in Manhattan, Kansas from two features, which are the hour of the day and the day of the year. This is the same example that we used in the video on regression trees. To be clear, this feature, which is the hour of the day, is encoded as a number between 0 and 23, and the day of the year is a number between 1 and 365. And then the response that we want to estimate from these two features is the temperature in Manhattan, Kansas. Our training data are the temperatures from 2015, and our test data are the temperatures from 2016. This is what the training data look like. So the x-axis is the day of the year. So this is the winter, where it's colder. This is the spring, where it starts getting warmer. This is the summer, and this is the fall. And I guess a little bit of the beginning of winter. The y-axis is the hour of the day. So this is the night. It's typically cooler. This is the morning. This is the middle of the day. And this is the evening. Okay, so hopefully this gives you an idea of what the data look like. These are our training data. We're interested in models that perform well for our test data, which is temperatures from 2016. As you can see, the general structure of the data, maybe I will erase this so you can see it better. The general structure of the data is similar in both years, but not exactly the same due to random fluctuations from year to year. Okay. Great, so this is a regression tree that was fit to this data in the way we described in the video on regression trees. What's important to remember is that the regression tree provides a nonlinear estimator of the temperature, which is associated with this binary tree. Each of the leaves of the tree represent a subset in a partition of the feature space. So this leaf corresponds to days before smaller than 65. This other leaf is days between 65 and 144. These other leaves, are days between 144 and 296, exactly, where the hour is smaller than 8. And this one is the same, but the hour is larger than 8. And finally, this last leaf is days greater than 296. Okay, so this is a simple tree that has 5 leaves. Now, if we want to, and the way we estimate temperatures based on the tree is we average the training data corresponding to each of these subsets of the feature space. What we do is we average the training data inside each of these regions, and that is going to be our estimate corresponding to that region. Okay, so here you see for the first region, the average is minus 1.4 because it's the winter. This other region, it's spring, so it's 13.7. This is summer in the morning, 19 degrees. Summer, rest of the day, 25 degrees. Well, in the morning and in the night, this one. And then finally, fall, beginning of winter is 6.7 degrees. Okay, and now if we want to estimate a temperature from the two features, here's an example, August 19, which is the day 251 at 3 a.m., which is hour 3. Then we traverse the tree to find the corresponding leaf. So here, D is greater than 65, it's smaller than 296, it's larger than 144, and H is smaller than 8. So this gives us our estimate, which is 19 degrees. As you can see, this estimate is interpretable. We know that we're saying that the temperature is 19 degrees because one of the features, the feature D, is between 144 and 296, and the other feature is smaller or equal to 8. So this all sounds great, but let's take a look at an important limitation of trees, which I've already mentioned. Here is a tree with 11 leaves. And the structure it learns from the data actually makes a lot of sense. You know, it's warmer during the day in the summer. It's, in general, it's warmer during the day, colder at night. This is the day, this is the night. It's colder in the winter than in the summer. Everything makes a lot of sense. Now take a look at this tree with 15 leaves, which captures more structure, more granular variations in the temperature, but also has a small problem. Let's see if you can find it. You can pause the video if you want. If you've seen the video on regression trees, you already know about it, but this might remind you. So what happens here is that we see this stretch of the winter. Maybe I'll use another color. This stretch of the winter where suddenly it's warmer than right after. And that doesn't feel right because we know that during the winter, typically, the temperature gets warmer and warmer as we go towards the spring and the summer. So what's going on here? Well, what's going on here is that that particular year, indeed, it was warmer here for some reason, at that time, for some reason. During the day, we don't see the same thing in the night in the model, although we see a little bit of it in the data. But the problem is that that's spurious structure that might not generalize to the test data. And indeed, it does not. So here, when we compare the two models to the test data, what we see is that in this model here to the right that has 15 leaves, we don't see the same thing. So this part that is warmer in 2015 is not warmer in 2016. So indeed, this was a random fluctuation, as I suspected, that overfits the training data and won't generalize well to the test data. When we look at the training and test error for the tree on our data sets, what we see is that obviously the training error just goes down and the test error starts going down, but quickly when we have more than around 11, 12 leaves, it starts going up again because we're learning spurious structure that does not generalize. So the tree overfits. This is by no means an exception or like a very special case. This often happens with trees. We have this problem where simple trees underfit, they don't capture enough structure, and complex trees that do capture structure overfit very quickly. This is a well-known problem. So what can we do to address this problem? What we can do is we can combine multiple simple trees which are going to underfit individually, but hopefully their combination is going to give us a complex model that does not overfit as much as individual trees. This is the motivation behind the three strategies that we're going to learn about today. These three strategies for combining multiple trees are called bagging, random forests, and boosting. So the first strategy that we're going to discuss is bagging. Let's give some motivation. Imagine that you have a response y, which we're going to model as a random variable. That's why there's this squiggly line on top. And you have access to b different models. Let's say 10 different models, for example. Each of the models, we're thinking about trees, that's why the models are called T, gives you an estimate that is equal to the response, which is great, but also has some additive error, which we're going to denote by ZB. All right? We're going to assume that these errors are all independent. They're zero mean, so these models give us an unbiased estimator, and the variance is equal to sigma squared. Because the mean is zero, the variance is going to be equal to the mean square. So the mean squared error of each of these estimators with respect to the response is equal to the variance of this guy, because this guy is zero mean, and hence equal to this. Okay, so that's going to be the mean squared error. Let's make it clearer. If we take the response and we subtract the estimator provided by the model, by each individual model, we're going to be left with this. And the mean square of this is just equal to its variance, because it's zero mean, which is sigma squared. So that's the error that we get if we apply each individual model. But now what happens if we build an ensemble of these B models by just averaging them? So we sum all of them and then we divide by the number of models. Let's take a look at the mean squared error that is achieved by this ensemble. So now here we are averaging y b times. So basically this is just equal to y plus the average of the errors, which is going to cancel with y, right? With the response. So here we're going to get this cancellation, and we end up with this, with the mean square being equal to the mean of the square of the whole average. Now, by linearity of expectation, this guy can come out, and it's going to come out squared because there's a square here. After that happens, we have the mean of this sum of random variables that are the CBs. We have the mean of the square of this sum, but the sum is zero mean because each of the individual errors is zero mean. So the whole sum is also zero mean, which means that this is equal to the variance of the sum. And remember that 1 over b squared has come out. Where am I going with this? Well, now, if it is true that the errors are independent, then the variance of a sum of independent random variables is just equal to the sum of the variances. So here we're summing each individual variance, which is equal to sigma squared. We're summing b of those, and we're dividing by b squared. So the result is that the error of the ensemble is sigma squared divided by b. So this decreases linearly with the number of estimators that we're combining to build our ensemble. So this tells you that if you have access to different models that have independent errors, you should average them, you're going to get a better model. And this is a very powerful idea in machine learning. Of course, there's a catch here, which is that the errors have to be independent. And this is often difficult to achieve. But still, this is a very powerful idea. Okay, so let's get back to bagging. In bagging, we want to combine trees that are learned from different data. But now you might say, wait a minute, where do we get different data sets? Because usually the way regression works is that we have a training set, and that's what we can use to train our model. This is a great question. What we're going to do is we're going to resample the available training data. This idea is known as the bootstrap, and we have already discussed it in the context of estimation of population parameters, where we used it to estimate standard errors and also to build confidence intervals. Here, we're going to apply it to build ensembles of trees. Let's remind ourselves about how bootstrapping works. Imagine that your data look like this, x1 to xn, and you want to obtain a bootstrap dataset. The way you do it is you sample indices between 1 and n. Okay, you sample indices between 1 and n independently and uniformly with replacement, and then you use those indices to resample your data. Okay, in case you get a little bit confused by this notation, let's just look at a simple example. So imagine that our data, we have 4 data points. Usually we would have many more, but for the sake of the example, let's imagine that we have 4 data points. And by the way, well, okay, let me start with that. We have 4 data points, and now we want 4 bootstrap samples. We're always going to end up with the same number of samples as in the original dataset. In order to obtain these 4 bootstrap examples, we sample an index between 1 and 4. So K1 happens to be 2, K2 happens to be 1, K3 happens to be 2, and K4 happens to be, let's say, 3. Our bootstrap dataset is going to be equal to X, and now I'm going to look at this index, and this is the index I'm going to use, X2. B2 is going to be equal to X1, because that is the index that we have sampled. B3 is going to be equal to X2 again. So see that we're repeating some of the samples. And B4 is going to be equal to X3. And notice that X4 is not included. We're also going to not include some of the samples. This gives us a new bootstrap dataset. If we're interested in regression, then instead of just X1, X2, X3, X4, we would have X1, Y1, X2, Y2, X3, Y3, and X4, Y4. And now in our bootstrap dataset, we would also incorporate the corresponding response. So the first bootstrap pair would be X2, Y2, the second one would be X1, Y1, the third one would be X2, Y2 again, and the fourth one would be X3, Y3 again. You have to notice that the feature vectors are always assigned to the same response that was observed in the original dataset. Okay, so this is how we use bootstrapping to obtain bootstrapping regression training sets that we can now apply to fit different models. And in fact, bagging stands for bootstrap aggregating. What we do in bagging is we fit trees to datasets produced via bootstrapping. Given the training data, we resample n data points independently and uniformly b times. For each of those times, we fit a regression tree or a classification tree, depending on which we're interested in. And then we just average those trees to produce the bagging estimator. So realize that in order to obtain our estimate for the bagging estimator, we plug in the new feature vector X into each of the trees, we look at their outputs and we just average them. It's as simple as that. Let's take a look at a visualization of this process. These are training data. And now I'm going to show you leaves, not leaves, I'm going to show you trees, or rather the partitions corresponding to different trees, and specifically with like the estimate in each part of the partition. And these trees are all going to have 5 leaves, so they're quite small. And they're all produced with different bootstrap datasets. So here's the first tree, this is the second tree, this is the third tree, and then we would do this over and over and over. For example, 32 times. And this is what the ensemble looks like. You can notice that the ensemble has quite a lot more structure than any of the individual trees. This is what the errors, the training errors, and the test errors look like for the individual trees in this ensemble that I just showed you. So as you can see, there is quite a bit of overfitting. When we compute the bagging estimator, what we see is that, first of all, the training error is much better. This means that this ensemble of 32 trees is able to fit the whole training set better due to its added complexity achieved by combining all of these simpler trees. And also, this allows it to improve its test error, which is better than most of the individual trees. Okay, so this improvement in the training error also translates to improvement in the test error. It's important to point out that there's less error, but now we have lost something. We have lost interpretability. Now it's much more difficult to say, oh, the estimate here is because, this feature is between this value, and this other feature is between this value and this value. We cannot do that because we would have to say that for each individual tree among the ensemble of 32 trees. So suddenly, the reason why the model is producing that specific estimate cannot be described in this really succinct way, which we get with trees. So the model is much less interpretable, but it works better. Now we're going to look at random forests, which are motivated by a limitation in bootstrapping. So you might have noticed that our bagging trees looked all quite similar. When you do this bootstrapping, the datasets are not that different from each other, and you end up with trees that are pretty similar. For example, tree 1 and tree 2 here, and tree 3 here are almost the same. So this means that the ensemble is averaging trees, many of which are quite similar to each other, so it's not able to learn as much structure from the data as it perhaps could. This also goes back to the fact that when you ensemble, you want errors that are as independent as possible, and if you have essentially the same estimator, then the errors are going to not be independent at all. So the idea here is that we want to modify the tree construction to promote more variety in these trees that are trying to fit the training data. So the resulting estimator is called random forest, which is a very cool name. And the idea is similar to bagging with a key difference. So again, given training data, what we do is we bootstrap, we resample exactly in the same way as bagging. We resample n data points independently and uniformly b times. And now for each of these b bootstrapped datasets, we're gonna build a tree. But when we build the tree, we're going to apply randomized recursive binary splitting. I will explain in a moment what that is. And that is going to give us more diversity in the trees. And finally, exactly like in bootstrapping, we're just going to average the resulting trees to obtain our random forest estimate. Okay, so what is randomized recursive binary splitting? We explained recursive binary splitting in detail in the video on regression trees, but let me remind you how it works. So the way we build trees is recursively, is by adding leaves one by one, or rather than leaves, by adding bifurcations to the tree. And every time we add the bifurcation, we try to improve the error of the tree as much as possible. This is a greedy scheme that I was struggling to find the word, but basically iteratively, that's what I was looking for, grows the tree iteratively. So you start at the root, you decide on a bifurcation, then another bifurcation, then another bifurcation, and so on and so forth. And the key question is, where do you add a bifurcation so that you get two leaves where there was only one? Equivalently, which region of the partition induced by the tree are you going to cut up? So in this example, we have 1, 2, 3, 4 regions associated with these 4 leaves of the tree. Now we want to cut up one of these guys in order to produce 2 new leaves and therefore a tree that is more complicated and fits the data better. What we do in recursive binary splitting is we look through the options. So here we could split each of the 4 regions according to the day of the year or according to the hour of the day. If we split according to the day of the year, then we still have to decide what threshold to use. Do we cut here or do we cut here? And in order to decide, basically we look at the resulting decrease in mean squared error that is going to be achieved by different thresholds. So this is what happens if we cut up the first region according to these different thresholds, the second region, the third region, and the fourth region. And what we observe is that the best thing to do, the greatest decrease in mean squared error is achieved by cutting the third region, roughly here maybe. Now that's not the only option, right? We could also use the other feature. We could also use the hour to cut up the regions this way instead of that way. And indeed, this is the best thing to do. If we cut the third region approximately around 8, so approximately here, this is what achieves the best decrease in mean-squared error. That's the best thing to do. Okay, so we decide that that's what we're going to do. I thought I had a picture here, but let me just draw the picture myself. What we do is we say, okay, the best thing is to divide this region between h smaller or equal to 8, h greater than 8. And now we're going to get two new regions, which we're going to average. We're going to take the training data in those two regions, we average them, and that gives us the estimates associated with these two nodes. And that's how we grow a regression tree to fit it to a training set. Now, what is randomized binary splitting? Well, the only difference in randomized binary splitting is that at each decision of where to add a bifurcation, we only consider a random subset of features. So I was using bifurcation a lot. Split is much easier to say. I don't know why I didn't just say that. So here, for example, when we're deciding, we would not, like from time to time, we would only consider this feature and not consider this one, for example. So that would give you a different tree, right? Because here, normally you would choose this guy, but now you cannot consider it. So then you would split according to this guy. And other times, at other splits, randomly, which would decide to only split according to the hour. If we had more features, maybe we would use, if we had like 10 features, for example, maybe we would use 5 of the features at each split, and we would select those features randomly. Every time, a different set of 5 features. In our example, what we're going to do is 80% of the time, we just decide between the two features, and 20% of the time, we're going to pick a random feature. This is because we only have 2 features instead of, let's say, like 100. When you have 100 features, a very popular strategy, when you have not 100 features, when in general you have D features, so tens or hundreds of features, a popular choice is at each split to choose square root of D. So if you have 100 features at each split, you would choose 10 random features that you would consider to split the tree and add these 2 additional leaves. And then at the next step, you would choose 10 other features and so on and so forth. So these are the trees that were produced by bagging. I'm going to show you the trees produced by our random forest strategy using the same bootstrapping sample. So tree 1 would use the same bootstrapping samples as the original tree 1, the one from bagging, sorry. So that I think I made that more confusing than it should be. But basically for random forests, the first tree is going to use the same bootstrapping samples as this guy. The second tree is going to use the same bootstrapping samples as this guy, and the third one, and so on. And these are the trees produced by the random forest. We see that they are very different. Specifically, the first one is very different because at some point it was forced clearly to use the hour of the day because the day of the year was not available for that split. And because of that, when we look at the ensemble of 32 trees produced in this way, with this randomized splitting, we see that it has more structure, more because of the additional variety than the original, than the bagging estimate. Okay, you can see it especially in this region, where here there's more structure that has been learned. So now let's compare the errors achieved by both the individual trees and the ensemble to the ones achieved by bagging, which we had already looked at, and you can see them here. What we see is that, first of all, the training errors, at least some of them, are larger. And this makes sense, right? Because the trees that were fitting to the training data, they can't use some features from time to time. So then they're going to fit the training data worse. However, interestingly, when we look at the ensemble, it fits the training data better. And the reason is this additional structure that is able to learn by this exploiting these trees that individually don't fit the training data as well, but they are different from the original tree. So they're learning new information that can be exploited to improve the whole ensemble. And that's the key idea behind random forests. We see that this results in an estimator that also generalizes better to the test data than the bagging estimator because, again, of this additional structure that is learned thanks to the higher diversity in the individual trees that form the ensemble. All right, so now we're going to learn about our third strategy to combine trees, and this strategy is actually very different to the one leveraged in bagging and in random forests. So in bagging and random forests, we combine independent trees, or they're not really independent, but as independent as possible. At least that's what we're aiming for. In boosting, we aim for the opposite. We want trees that are as complementary as possible, with a caveat that is very important that I will explain in a moment. But that's the philosophy, okay? We want complementary trees. So let's see first how the boosting structure would look, the boosting strategy would look like if we just apply it naively. We want to just fit complementary trees to the data. So we start with our data. We fit a tree that looks like this and has 5 leaves and hence 5 regions corresponding to each of the leaves. And now we subtract the tree from the data. And this gives us a residual. This is the error we're making when we use this tree to approximate this data. And now what we can do is fit another tree, but to this residual, so that when we add the 2 trees together, they're going to approximate the data better. And we do exactly that. Okay, so this is what the original data look like. This is the residual after subtracting the first tree. This gives us this new tree that approximates the residual. And this is the boosting model obtained by averaging the first and the second tree. So this boosting model is going to approximate the data better because this tree approximates the residual and the original tree approximated the original data set. Okay? And now we repeat this. We take the data, this is the residual after subtracting the 2 first trees. So the boosting model obtained by averaging the 2 first trees. We fit a tree to that residual and we get this new boosting model. And we basically repeat this on. And I want you to look at the trees. I want you to look at what these tree estimators look like. And what you will see is that they start capturing very, very intricate structure in the training data. So in particular here, they capture a few days in the winter, and this is translated into the boosting model that starts becoming very, very intricate. This is a great thing. This is already with 10 trees, 20 trees, as you can see, individual days are being captured here, 30 trees. This gives a boosting model that actually approximates the training data really, really well, but it's also very, very intricate. In particular, we see some signs of overfitting, such as here, as we had discussed for the individual tree. Why? Because we see this in the training data. When we look at the training and test error of this naive boosting strategy, where we're trying to improve the model by fitting these complementary trees to the data, we see that it fits the data incredibly well. The training error goes down very rapidly, but the generalization is really poor because we're overfitting very intricate details of the original dataset. So this doesn't work at all. We're not going to give up. We're going to think a little bit about it. How can we avoid overfitting? Because there's a lot of potential here. We can actually learn a very complicated structure that could be useful, but the problem is that we're overfitting too quickly. So what we can do is we can scale down the contribution of new trees. Now there's a very big literature on boosting algorithms, and there's different strategies to achieve this that can get quite complicated, but many of them rely essentially on this key idea of just scaling down the contribution of the new trees that you're fitting to these residuals. Let's see what I mean by that. We're going to use a very, very simple approach. We're going to take our new tree and we're going to multiply it by a small constant gamma that we're actually going to just set to 0.1. This is the typical parameter that you should choose based on some held out validation data, but here let's just fit it to 0.1 for simplicity. So now we have our data set. We fit our first tree. It's exactly the same as in our first try. We get, but now we weight it. We're going to multiply it by 0.1. Okay, so we take this tree, was fit to this data, but here we multiply by 0.1. So now this tree cannot fit the data as well as it could when it wasn't multiplied by 0.1. And when we compute the residual still preserves a lot of the structure in the training data, which is, as we will see, is going to be a good thing. Initially, it's not that great because now we're not approximating the data as well, but we're going to repeat this over and over. So now we have our residual from our first tree. We're going to fit another tree and we're going to again scale it down. And now our boosting model is the scaled down version of this tree plus the scaled down version of the first tree. And this gives us this boosting model that is quite scaled down, so it can still not approximate the data very well. Now we're going to repeat this over and over. Third tree, fourth tree. I want you to notice that these trees now no longer try to fit individual days because of the fact that we have not subtracted kind of individual days. We cannot subtract individual days from the residual with this procedure because they're all scaled down. So they are able to learn more global features, or they're forced to learn more global features perhaps because this residual is not as structured as in our naive strategy. We're just removing completely the tree estimates. Hopefully that makes sense. And you can see that indeed these trees now look like capture much more global structure than the naive boosting trees. The model, little by little, is growing. Again, because we're scaling each individual tree, the model can only grow little by little. By the 10th tree, it looks like this. 20th tree, 30th tree, this already looks as if it could fit the data. And we see that the model is much smoother than in the case of the naive boosting strategy, where we're fitting essentially almost individual days with a lot of the trees. When we look at the training and test error of the boosting strategy that uses this scaling down to prevent the individual trees from overfitting as much, then we see that at first, both the training and the test error are terrible, of course, because we're using these very scaled down trees to try to approximate the data, but eventually we actually get very good results. And in fact, boosting algorithms work extremely well for practical problems where you have tens or hundreds of features. They're essentially state of the art for many practical problems. So now when we compare it to when we compare bagging, random forest, and boosting, actually, we only compare random forest and boosting. This is a typo because otherwise the graph would be too busy. Random forest in general overperforms bagging, and we saw that in a previous graph. And now we're going to compare random forests and boosting. What we see is that the naive boosting strategy is terrible. So this is the test and the training error, so that it clearly overfits. It achieves the best training error because it's really fitting every intricate detail in the training data, but of course it does not generalize. Its test error is around here. Random forest performs quite well. So this is its training error and its test error. But, not for this specific data set, boosting performs much, much better. So this is the this is the training error of boosting. Obviously, it doesn't fit the data as well as the naive boosting strategy, but it does fit it better than the random forest, and this translates to better test performance here, actually significantly better for this dataset than random forests. In other datasets, it's possible that random forest could outperform boosting. Both methods are very good for many problems in practice. All right, so what have we learned? We have learned how to build complex models combining simple models. In particular, regression trees. The same procedures can be easily adapted to build complex classification models. We're now in the realm of machine learning because we have given up, this is something that I was going to say later, but I will say it now. We have given up interpretability and we're just trying to get very good performance with a complex nonlinear model in held out datasets. That's really what we're pushing here. And this can be achieved with 3 ensembling strategies: bagging, which averages models fit to bootstrap data; random forest, which averages randomized models fit to bootstrap data; and boosting, which builds complementary models by carefully fitting residuals. There are several take-home lessons from this. First, you can use random sampling to try to fit different models to the same data set. Second, you can use randomization to try to increase the diversity of those models, as in random forest. And third, in the case of boosting, when you're learning models that can fit the data very, very well, you have to be careful to regularize them to prevent them from overfitting, and then combining those models can be very powerful. There's an important trade-off here as we move from statistical models that are very interpretable to machine learning models that are very complex and powerful, and that is usually that we lose interpretability. We don't lose it completely in the sense that you can always compute sensitivities, basically how individual features affect the model output, but it's much more difficult to describe in general the regression function in terms of, we produce this estimate because this feature is between this value and this value, which is trivial to do with trees. And that's all I got. Thank you. I thought that's all I got, but I just flipped just in case. And it's good to remind ourselves that overfitting is a constant threat. So here, I guess the philosophy is we combine a lot of models to obtain more complex models that can fit the data, but we can easily run into overfitting if we're not careful. All right, and now that is all I got. Thank you very much.